de Moivre's theorem is a crucial theorem when it comes to complex numbers. And the reason for that is because it highlights the use of complex numbers in doing real calculations that would otherwise be more difficult. And in this video, we're going to particularly focus on how we can derive trigonometric identities using de Moivre's theorem. But before we get into the heart of the video, let's first state what de Moivre's theorem tells us. It states that for a whole number n, we have that cosine of theta plus I, the imaginary number, times sine of theta, everything to the power of n, a whole number, is equal to cosine of n times theta plus I times sine of n times theta. And the way you can understand this formula is by seeing it as a direct consequence of Euler's formula, which states that e to the I theta is equal to cosine of theta plus I sine of theta. And so obviously when we raise an exponential to the nth power, so when we get e to the I theta to the power of n, well, we just multiply the exponents, and so we get e to the I n theta, which is this expression on the right of de Moivre's theorem. However, in this video, we'll favor the trigonometric notation of de Moivre's theorem, and the reason for this is because if we further scrutinize the intricacies of this formula, we realize that we can derive the formula for cosine of n theta and sine of n theta if we know how to expand the expression on the left using the binomial theorem. For example, if we want to find the sine of 3 times theta, we need to use de Moivre's theorem in trigonometric form before we replace n by 3. And so we have that cosine theta plus I sine theta to the power of 3 is equal to cosine of 3 theta plus I sine of 3 theta. And our goal, of course, is to find sine of 3 theta. But first, let's expand this using the binomial theorem. And so we get that cosine to the power of 3 of theta plus 3, can't forget about the binomial coefficient, of cosine squared of theta times I sine theta plus 3 times cosine theta, and then we have I sine theta to the power of 2, so I squared is negative 1, and therefore we have a negative over here, and then we have a sine squared theta. So let me get rid of the plus sign, and afterwards we have sine cubed of theta, and all that is equal to cosine of 3 theta plus I sine of 3 theta. So we have an equality over here, and when it comes to complex numbers, the thing you have to remember is that two complex numbers are equal if and only if their real parts and imaginary parts are equal. So let's call this expression on the left L and the expression on the right R. And L and R are both complex numbers. And so these complex numbers are equal if and only if the real part of L is equal to the real part of R. And similarly, the imaginary part of L is equal to the imaginary part of R. And why did I need to remind this? Well, because here the imaginary part of the expression on the right is just sine of 3 times theta. So therefore, the imaginary part of this expression is equal to the imaginary part of the expression on the left, and therefore sine of 3 times theta is equal to the imaginary part on the expression we have on the left. And therefore, we have that sine of 3 times theta is equal to, what is the imaginary part of the expression on the left? Well, it's 3 cos squared sine theta plus, oh, I made a mistake. I forgot the I when I expanded here. So it should be a negative I. So we should have negative I minus sine cubed of theta. As a little aside, it's always nice to factorize here by sine of theta. So in other words, when we want to determine an expression for sine of n theta, it's always nice to have a function of cosine theta times sine theta. And this is associated with Chebyshev's polynomials, which I won't expand in this video, but maybe in a later video. And so now we have that sine theta times 3 cosine squared of theta minus sine squared of theta. But sine squared of theta is just 1 minus cos squared of theta. And therefore, we get sine of theta times 4 cos squared of theta minus 1. And therefore, this is the formula for sine of 3 times theta. In a nutshell, we can derive trigonometric identities using de Moivre's theorem. And the way we do that is by using the trigonometric version of de Moivre's theorem. So we neglect the exponential form. The crux of the problem essentially boils down to expanding this power over here using the binomial theorem. And afterwards, we get an equality between two complex numbers. And therefore, we can use the fact that the real and imaginary parts in a complex equality have to be equal to each other. And hence, we can derive the formula for cosine of n times theta and sine of n times theta. In this video, we looked at sine of 3 times theta, but if we looked at cosine of 3 times theta, well, this corresponds to the real part of this expression on the right. And therefore, cosine of 3 times theta would be equal to the real part of the expression on the left. In other words, cosine of theta to the power of 3 minus 3 times cosine theta times sine squared of theta. And there we have it. This is how we use de Moivre's theorem to derive trigonometric identities.